Welcome to Physics for Architects. Please watch this video and answer the online questions before the first day of class. Welcome to Physics for Architects. So keep in mind that this course is offered every other year. So Physics 8 will next be offered in fall 2023. So Physics 8 and Physics 9 alternate. Physics 8 is Physics for Architects 1 and Physics 9 is Physics for Architects 2. So this course mainly covers the branch of physics called mechanics, and it's intended mainly to leave you in excellent shape to take someday an architectural structures course if you are in the architecture program. Or if you're not in the architecture program, if you learned mechanics before in high school, or even if you didn't, you'll come away with, I think, a firmer grasp of Newton's laws of motion and how to apply them and how they connect to what keeps architectural structures standing up. So Physics 8 covers a pretty similar set of topics to other introductory college physics courses like Physics 101, which is mainly for pre-meds, or Physics 150, which is mainly for engineers, or Physics 170, which is mainly for physics majors. So what makes it Physics for Architects? So one thing is that typically about half of the students in this course are architecture majors. So you're in the undergraduate architecture program at UPenn, or a closely related program like the Fine Arts program or the design program. Having your own course lets us tailor the course to your interests and to your background. So I have sat in on many of your studio critiques over the years, so I've got at least a little bit of idea what you do in the courses that take up the bulk of your time. And I also certainly know how much time you put into those courses. So I've tried to learn over the years how to make the course connect with you and how to make it compatible with what you do. For example, we don't meet on Tuesday and Thursday afternoons, even though that would be a convenient choice, because I know that those of you in the architecture program are in studio Tuesday and Thursday afternoons. So once we've covered the basics of Newton's laws of mechanics, we'll spend several weeks applying what we've learned to study topics related to architectural structures. So we'll learn how to analyze trusses, which are those kind of triangular shaped things you might have seen on railroad bridges. You know, anytime you see things kind of broken up into triangles, particularly on an old railroad bridge, that's typically a version of a truss. So we'll study topics related to architectural structures like trusses, cables, beams, and so on. And I think this is a fun way to connect the physics with applications, and they're applications that you'll see again if someday you take a structures course. So I know that you're accustomed to working together, and I know that's true of the students in the undergrad architecture program, and then we also often get a lot of students from the Huntsman program, and I know that you're really accustomed to working together on case studies in that program. So we will do most of the learning in this course cooperatively in small groups. And I think you'll like that, and I think in particular this year, when we're just coming back from a year or so of not being able to see very much of each other, I think it will be fun to be able to spend the time really learning together in small groups. For a long time, architects have been designing structures to span spaces. You might ask, is physics relevant to this pursuit of spanning spaces with structures? I think it is. So let's make a model of a bridge, which is just a plank being held up on two ends. And this is actually also going to introduce us to this concept of models. And physics often uses models to take a real-world problem and to turn it into a form that is amenable to pencil and paper analysis, or somehow to take a complicated problem and to simplify it into a form that we can understand more readily. So I'm going to show you the demonstration in a moment. Let me just give you a preview of what it's going to be about. So we're going to have basically a wooden plank, and that wooden plank is going to be supported by two scales. I'm going to draw it as if we were drawing a simply supported beam just for fun, but really the two supports are the same in this demonstration. So we have a plank here, and the plank is supported by two scales, each of which reads out in kilograms. And the question is, how is the load, the weight of the plank, shared between the two scales? And first we're going to put the two scales at the very end, and then we're going to move one of the scales closer to the center, and we'll ask, how does what the two scales read change as we move one of these scales around? And maybe how do the two readings together relate to the weight of the plank? Okay, so in physics, we often use models to take a real-life situation and simplify it into a form that we can easily analyze, or sometimes that we can visualize with simple pieces. So my model of a bridge is going to be this plank and a couple of scales to support it. So I claim that this is an 8-kilogram plank. So we have here a scale that measures kilograms, and just to show you, it's basically an 8-kilogram plank. I'll put the plank onto a single scale, and I think you can see that it weighs about 8 kilograms. It doesn't have to be precise, but okay, it's a little less than 8, so roughly 8 kilograms. So we're rounding a little bit. So now my model of a bridge is going to be, well, first of all, let me remove this and replace it with something that's a little pointier, so we can concentrate the weight in one place. I'm not showing you the faces of the scale, so this way you can see the scenario. So we're going to, and I'm going to redo this in a moment with the scales so that you can see them. But, okay, so you can see I have the length of the plank marked out, 1, 2, 3, 4 units. And basically I have the two scales holding the two ends. And so the question is, how much weight, what does each scale read? So we put the whole plank on one scale, and so we want to ask, how much of a load does each of these two supporting members have to support? If we have the bridge deck here and it's supported by, let's say, a column on each end. And so you can kind of think it through in your mind's eye before we reveal. And I'm not going to give you any systematic way to understand this today, so I'll show you what the result is that the scale reads, but I won't try to give you any way to think it through. And I deliberately don't want to give you any way to think it through for two reasons. One is that we will see very systematically a couple months from now how to analyze a situation like this using the concept of force and the concept of torque. By the way, if you go on to take an architectural structures course, maybe in your senior year at Penn, Professor Farley will want you to come into that course really being highly adept with three concepts from this course. One of them is forces, another one is torques, which he and engineers call moments, but we'll say torques in this course, we'll say moments, usually in architectural structures, and vectors, okay, so forces, torques, and vectors. And we will go through those three ideas in a lot of detail as the course goes on. Anyway, so I guess this is so once we've covered especially forces and torques, we'll be able to analyze a situation like this systematically. But for now, we'll just see what the result is, and then on the first day of class, you will work through very similar, like a scaled down version of this same demonstration, and you'll try to figure out with within your group of 3 people at your round table what the rule is that governs how the weight is divided between the two scales. So I don't want to give it away. I want you to see if you can figure it out, and then we'll see later in the course systematically, kind of rigorously, how it works. So let me turn the two scales around. So I want to pause for a minute and guess. So remember, the weight of the plank is 8 kilograms. Oh, by the way, the mass of the plank is 8 kilograms. There's a little bit of a semantic issue. Does a scale measure mass or does a scale measure weight? Again, we haven't gone far enough in the course for me to be able to tell you what all of that means, but
mass, measured in kilograms, is telling you how much stuff there is, essentially kind of like how many atoms and what kind of atoms, whereas weight is a unit of force, which is saying how hard do I have to push to keep this thing up in the air. So a scale, actually, a spring scale actually works by squishing a metal spring, and just about all substances in nature, if you apply a bigger and bigger force to them, they squish more and more, and then the scale reads out in proportion to how much it's squished. So it's actually measuring weight, not mass, but it's reading out in kilograms, which are a unit of mass. I'm just warning you about that. You'll think this through more systematically a couple of weeks from now. So let's see what happens when we turn the scales around so that you can read the dials. And it looks as if, instead of one scale reading 8 kilograms, or just under 8 kilograms, instead we have two scales, each one reading just under 4 kilograms. So it appears, when configured symmetrically like this, each scale seems to get half of the total weight of the plank. I'm just showing you the answer. You're going to talk it through with your classmates on the first day of class. Now let's look at one other scenario while we're here. Envision in your mind's eye what's going to happen if I take this scale and I move it to this point. So here's, you could say 1, 2, 3, 4. So this is the halfway point. This is, say, the 3/4 point. So I'll leave this one out here at the end, but I'm going to move this one from the end into the 3/4 point. And the question is, how will the readings on these two scales change? And maybe one way to build your intuition about whether they'll stay the same or one of them will get bigger, if it's close to the beginning of the school year, so if you have a memory of helping your friend or your roommate carry a heavy piece of furniture, you remember what happens if both people are on the end versus if maybe one person is on the end and one person is a little bit farther in, like this. And if you have two people working together cooperatively and one of them is stronger, you might imagine in your mind's eye, well, do you put the stronger person out on the end, or do you put the stronger person in a little bit toward the center? I don't want to say too much because I want you to figure it out and think through what the rule is when you try it yourself in class. But I'm just putting that into your mind's eye for intuition. Okay, now let's see what happens if we move this scale over to the basically, instead of being all the way out, it's at this 3/4 mark. So, whoops. And you can just make a note. It seems like this one now reads a larger value than it did before. This one now reads a smaller value than it did before. You could also just make a mental note of what the two numbers add up to, and I'm not even going to say it, just make a mental note of what the two numbers add up to. Make a mental note of which one is bigger. And then if you really want an extra challenge, you could make a mental note of the ratio of the two numbers and see if you can make sense of that. And I do really hesitate to give too many hints at this stage, but you could note how far this scale is from the middle, and you could note how far this scale is from the middle. But that's, now I've already said too much. Okay, so again, in physics, sometimes we like to take something real life, like a bridge, and simplify it to a form that we can play with classroom models, or that we can analyze with simple equations. And so this is an example of modeling a bridge and modeling how the the weight of the bridge is distributed between its supports as we move the supports around. Okay.
Okay. Now, the next thing we're going to do is we're going to use two different models. Okay, so again, we said physics often use models. We're going to use two different models to demonstrate the physics behind the 1981 Hyatt Regency walkway collapse in Kansas City. And if you're curious, you can pause to glance at the Wikipedia article. So here is a drawing of the skywalk taken from Henry Petrosky's book. And there is okay, so this is a fourth floor walkway, and this is a second floor walkway, and then each floor of this walkway is connected to the ceiling by some really long metal rods like this that basically go from ceiling down to the lowest level. And I actually say it's a little bit analogous to a person hanging on to a rope that's suspended from the ceiling. But, okay, and then here, we'll just say this is like the ceiling, so it's sort of this fixed surface that's supporting everything. And the question is, how does each one of these floors connect itself? How does this floor and how does this floor connect itself to these metal rods that are hanging from the ceiling? And the folks who built this structure on the construction site decided that it was an incredible nuisance to try to connect to the same threaded rod going all the way up to the ceiling. So instead, what they did on the construction site is they connected the top floor to the ceiling, and then they connected the bottom floor to the top floor. And let's say we did the same thing over here, we did the same thing over here, and so then we'll erase this original connection that the architect drew. So the architect said, well, you should have a threaded rod going all the way from the ceiling down to the floor, and then each of these suspended walkway levels should connect to that same threaded rod. And what was actually done on the construction site, because it was a lot easier to, is this was a relatively short cable going from the ceiling down to the top floor, and then there's a cable going from the top floor down to the next floor below it. My analog for this is, imagine this top floor hanging onto a rope, and then imagine that there's the friend, the lower floor wants to hang onto the same, well, wants to hang from the ceiling also. So one option is I grab the rope over here, and then my friend grabs the same rope down below me. In that case, I think I'm carrying my weight, my friend is carrying her weight. The other option is, well, I'll grab onto the rope up here, and then my friend, instead of grabbing onto the same rope, she grabs onto my feet. And so you can then imagine what happens where I'm trying to grab onto the rope, because my hands have to hold not only my weight, but her weight as well. So let's watch that demonstration now. I have it in two forms.
So we try hard in Physics for Architects to bring the physics to life for you, making sure that the physics connects to things that feel like real life instead of just being completely abstract equations on a sheet of paper. And then we have here built two different models of this skywalk walkway. On this side, we have the walkway structure as designed by the architect. Okay, so here we have the ceiling level in this model. Okay, so this is like imagine that this is actually some big girder on the ceiling. I know that it looks in this model the same as the floors, but let's instead pretend in your mind's eye that this is in fact a big girder bearing a whole bunch of weight from the ceiling. And then here's the upper level of the skywalk, and a middle level, and a lower level. On each side of the skywalk is a threaded rod. And we've modeled the threaded rod in this context. So remember, in physics, we often use some kind of a model to simplify something. So our demonstration model of this threaded rod is a wooden dowel. And so there's one long threaded rod here, and there's one long threaded rod here. And then you say this is the upper level of the skywalk. So this bridge deck is represented by a piece of PVC tubing, and it holds itself to each threaded rod with this clothespin. Okay, so this clothespin represents a nut which is used to attach this deck of the skywalk to its threaded rod. So the threaded rod is represented by a wooden dowel, and the nut is represented by a clothespin. Why did we choose to use a clothespin? Because there's a maximum force that this nut can support before it will fail. And so we want to mimic the fact that as the load borne by this connection and the structure reaches its maximum value, it will eventually fail. So that's pretty easy to mimic by using the connection of the clothespin to the wooden dowel. Because you can imagine that there's only so much weight that can be borne by this clothespin hanging onto the wooden dowel here. Okay, so here's a clothespin mimicking a nut, wooden dowel mimicking a threaded rod, a piece of PVC pipe mimicking the upper bridge deck of this skywalk. Then here's the middle level. And notice the middle level is hanging on to the same threaded rod with its own pair of clothespins, or nuts in real life. And then here's the lower level, and it's hanging on to this same threaded rod, which is a wooden dowel in our model, with its own pair of nuts or clothespins in this model. So there's one continuous threaded rod going all the way through. Now, this is a really long threaded rod, like many meters long. So it's basically like a 2 or 3 story tall threaded rod. And you can imagine what a hassle it would be if you were building this on a construction site to maneuver these extremely long threaded rods and all of the structural components through them for each floor. So actually this is kind of a lesson in design. So the original architectural design, the engineering design, assumed that it would be built the way it was designed. It turns out that the way it was designed was a hassle to build. So I guess it's also worth thinking, how likely is it that what I've designed will be built the way I intended? Here's what the construction crew on site decided to do instead. Instead of one big long threaded rod, here's a short threaded rod from the girder to the top floor. So far, it seems to be analogous to this. But then, here's another short threaded rod from the top floor to the middle floor. Here's another short threaded rod from the middle floor to the bottom floor of the sky deck. And then the same thing on the other side. So whereas in this case, here's like a big girder up at ceiling level. So the top floor is holding its own weight. The middle floor is holding its own weight through that same pair of rods with its own pair of nuts here. The bottom floor is holding its own weight to the continuous threaded rod with its own pair of nuts here. But what's happening here is the bottom floor is grabbing onto this pair of rods with its pair of nuts or clothespins. But then if you look at the middle floor is grabbing onto this middle pair of rods with its pair of nuts. But so it's not only holding its own weight, this connection is holding not only this weight, it's also, if you think about it, holding this weight. And then let's look at this upper floor. So the upper floor has this rod from the middle floor coming up and being held with a nut here. And it has this rod from the middle floor being held with a nut here. And then it's being suspended from the ceiling with this pair of short threaded rods. So this nut down here that's holding the top floor to the upper threaded rod is holding not only this weight, but it's also holding this weight and this weight. Let's see what happens when we load these things up. Oh, and by the way, now what do you do when you create a spectacular new space with an amazing skywalk feature? You of course invite a bunch of people to come and visit it, and you have a big party with people dancing, and people are all over this, all levels of this bridge, dancing rhythmically to music. Okay, as they dance. So let's put some weight on the lower dance floor, or the lower level of the sky bridge. And this is as designed by the architect. And this is as built by the on-site crew. And then we'll put a little bit of weight on the middle deck here. So this is as designed by the architect, and this is as built on site. And then we'll put a little bit more weight, we'll put a little bit of weight, you know, some people, maybe some of them dancing, on the upper level as built, upper level as designed, and then the upper level as built. Oh my goodness. So it actually didn't take very much to see that the as-built version of this failed. And actually what's really important about this is where did it fail? And we see that the place where it failed is where the upper level grabbed on to the uppermost short-threaded rod, because that nut that the upper level is using to hold its own weight onto the threaded rod is in fact in this as-built design holding not only its own weight but also the weight of the two floors beneath it. So our model actually failed in just the right place. I think it's neat that this is like it's an easy to build model which then expresses the failure as it happened in real life. So this, to some degree, this is a good metaphor for what we do in physics. We take a kind of simple to analyze or simple to build model which expresses some key property of real life and puts it into a form that in this case is easy for us to build and see, but in more often in physics we put things into a form that's easy for us to analyze with pencil and paper equations.
You could see that instead of being one continuous rod, that in the version that was actually built and the version that collapsed, this was split into two rods, one going from the top floor to the ceiling and one going from the bottom floor to the top floor. And then you could see in our model that the place where the modeled structure failed was right here, which is where the top floor is trying to hang on to its threaded rod. And then let's see if we can think about why that makes sense as the place for the structure to fail.
Okay, you see in the background the aftermath of our model using wooden dowels of the skywalk collapse. And remember that where this model failed, which is pretty true to life, is the nut, actually the clothespin that represents the nut that held the upper skywalk deck onto the threaded rod, which is above the upper deck. And I told you that my hands are going to mimic that nut, and my body will mimic the upper deck, and then this rope will mimic the threaded rod. So let's see if I'm still able to climb a rope. It's always a little awkward for me. And let me see how high I can get on this thing. I don't have to be too high, but maybe it's more fun. Okay, so at the moment I'm hanging on with both my hands and my feet because it's easier for me. But of course, to mimic the demonstration with the skywalk, I should let go with my feet and only hang on with my hands. I can do that, but you can see it's a challenge for me, but I can do that. Okay, but now let's reflect again on what's happening with the Kansas City skywalk. So this is, so my body represents the upper deck. Now how about the lower deck? The lower deck will be a friend who's going to grab onto the same rope. So if we do it as the architect designed, my friend will grab the rope. I'll really cheat here. I'm going to cheat and stand on the desk because I'm 2 years older than the last time I did this demonstration. Okay, so in the way the architect designed the structure, I hang on to the rope up here with my hands, and my friend hangs onto the rope down here with her hands, and that's just fine. her hands are holding her weight, my hands are holding my weight. Now let's think about the way that the skywalk was actually built on site, which is different from the architect's design. And the way to envision that is to picture, here I'll make it easier for you to picture. So again, you can see it takes a little bit of effort for me to hold my own weight. Now imagine that my friend, instead of grabbing the rope with her own hands, imagine she instead just hangs onto my feet. So you've got my hands holding me to the rope, and then instead of just holding my own weight, I'm holding both my weight and her weight, because instead of grabbing the rope herself, she's grabbing my feet. So now imagine the struggle. So you can see the clear failure point will be that my hands can't hold on, because it's hard enough for me to hold my own weight, but my hands would have to bear, in addition, not only my weight, but my friend's weight at that connection between, right, because my hands represent the nut that connects the upper skywalk deck to the threaded rod. And this force, we don't know the word force yet because it's the first day of class, but we'll know the word force a few weeks from now. So the force between my hands and the rope, in the first case, just equals my own weight. In the second case, the force between the rope and my own hands has to equal my weight plus my friend's weight. And that's going to sort of exceed the design specification, and the failure mode is that my hands let go of the rope, or over here in our mock-up demo, the failure mode is that the clothespin holding the upper deck onto the threaded rod, or the dowel, lets go. And you saw the collapse just a moment ago. Okay, so what's the point of this? One point of this is that physics is relevant to architectural design. And another point of this is we're going, later in the course, after we've built up a physics toolkit, we're going to look at some little elements of architectural structure, and we will analyze the forces, and in some cases also these things called moments, the forces and moments, or the forces and torques, supporting each element of a structure. And in particular, if we go and draw a diagram for this scenario, we'll see that you can draw this thing called a free body diagram, component by component. And if we were to draw a free body diagram for this upper deck, we would see that the force between this upper deck and this threaded rod, or the force exerted on this upper deck by this threaded rod, was basically about twice what it was designed to be, which then led to the collapse, especially with the increased load of lots of people and lots of people dancing. Okay.
So you saw from my hands on the rope, and you also saw from where the wooden dowel and PVC pipe structure failed, that the problem is that whereas here was the original design with a single threaded rod, that's kind of like a single rope, and I'm the top floor, I'm grabbing onto the rope here, and then my friend down below is the bottom floor, and she's grabbing onto the rope there, and everything is fine. I hold my weight, she holds her weight. But then the way it was actually built is basically here's like the rope going up to the ceiling, and then my friend, instead of grabbing onto the same rope, my friend decides effectively to grab onto my feet. And then this connection, I would call this connection between the upper rope, the upper threaded rod, and the top floor. So in fact, this nut right here, which is the clothespin that failed in the first model, this sort of represents my hands trying to hold on to the rope. We'll learn a few weeks from now how to draw free body diagrams as a graphical method to analyze forces, and then later to analyze torques. But in any case, just the fact that the vocabulary word free body diagram appears in Henry Petrosky's book, I think tells you that the physics we'll study this semester has some connection to architecture. So he drew a force diagram to represent essentially how big is the force between, which is like how much it's pulling, how big is the force between the top floor and the top threaded rod, which is kind of communicated by this nut at the bottom of the top floor, where the top floor meets the rod. And his claim is that force is twice as big in the as-built version as it was in the as-designed version. And you can see that the threaded rod, which is connecting the top floor to the ceiling, pulls out of the kind of girder for the top floor. In the as-designed version, I'm up here, I hold the rope, my friend is down here, she holds the rope, my hands hold my weight, her hands hold her weight. And then here's the as-built method, where I'm up here, I'm holding the rope, and then my friend, instead of holding onto the rope herself, she holds onto my feet. And then you have to imagine, well, what happens here where my hands meet the rope? Like, are my hands holding just my weight, or are my hands holding my weight plus her weight? I'm Bill Ashmanskis. I'm the instructor for Physics for Architects. I've been teaching this course since 2011, so this is my 6th time teaching Physics for Architects 1, and I've also 5 times taught Physics for Architects 2. So one way or another, I've been teaching this course for about 11 years. The name Ashmanskis is a little bit tricky to pronounce, and it's also, even if you can pronounce it, it's a lot of syllables. So usually it's easier, I know that in architecture you often call your instructors, your studio instructors, by their first names. So you can call me Bill. I'm perfectly fine with your calling me Bill. If you're not comfortable with that, you can call me Dr. Bill. Some people like to say Dr. Ashmanskis. You're welcome to say that. I just find it to be an awful lot of syllables. So I teach physics and I teach electronics here in the physics department, and I design electronics for research projects both in the radiology department and in the physics department. So the design work that I do usually involves writing computer code, but sometimes I use CAD software for printed circuit board design. So to that degree, I can relate to all the time that you, if you're in the architecture program, spend using CAD software to make computer models of something that you intend to be realized in the real world. I grew up in the suburbs of Boston, where my dad built wood frame houses throughout my childhood. And I actually worked for him one summer. It was the summer before my senior year of high school. And that taught me a lot about what holds our houses up. So it sort of felt like destiny that I should teach physics for architects someday, after in so much of my youth seeing blueprints for houses and seeing half-built houses, and even working on building a whole bunch of interior partitions and a few exterior walls for houses one summer with my dad. So we're typically going to have a combination of reading textbook chapters and watching videos due on Mondays and Wednesdays. Some weeks it'll just be Monday. And doing that on your own time lets us spend most of our classroom time solving problems together in small groups. So stuff that's basically just information transfer, you'll do kind of asynchronously. And then stuff that's really assimilating and using and truly learning the material we'll do together. And that way I'm nearby, the TA is nearby, and your classmates are nearby, so that when something doesn't make sense, you can discuss it right away. You're not stuck being frustrated for very long. And I think it should be a more engaging way to really practice the material as you learn it. So, you know, just as if you want to learn to play the piano, if you want to learn to be a better athlete, you want to say what kind of coach would you hire to help you to do that, you don't just watch videos of your coach playing the piano or exercising, playing football, etc. You might watch somebody else do it at first to get the idea of what you have to learn, but then you only really learn it by doing it yourself. And so there's a difference between kind of the superficial knowledge that you can gain by watching somebody else do something or by reading about something versus the skill that you build up by doing it yourself. So the time that we spend together, where I and the TA are nearby and where you and your classmates are working together, that time is really, I intend for it to be spent on skill building, where you're really practicing and, making the ideas really make sense in your own mind, and checking whether your own mind is really able to work out an answer. So we won't have any midterm exams, but I don't want you to get to the final exam and say, I've never done anything that looks like an exam before in this course. And I also want to make sure that even though you're solving problems in groups, I want you to bear in mind that you are responsible for knowing how to solve, with your own brain, the worksheet problems that you're going to solve with your classmates. So even though you're approaching them cooperatively, you want to bear in mind as you work them through that you need to know how to solve them later when your classmates aren't there. That's especially true for the more basic problems. Maybe some of the trickier ones would be, difficult on an exam. But certainly for, most of the problems that we'll see on the worksheets, I expect you, once you've figured them out by talking them through with your classmates, I expect you to internalize that so that you, in practice, like maybe even don't look at your own answer and try to solve it again, making sure that you really understand it before you move on. So just to make sure that you really are, even though you're working in groups, that you really are able to build that skill with your own brain, about once every week or two after, and this is, well after a given worksheet has been collected and graded and handed back to you and you've seen how I solved the problem, we're going to spend the first 15 minutes of class on a closed book quiz that repeats, maybe with some minor edits, a problem, and it won't be a really difficult problem. It'll probably be a relatively easy or just medium problem from that worksheet, so that we just make sure that you form a habit of keeping your own mind accountable for what you're learning, even though the learning is cooperative. And I think that doing it that way, like just spaced out with, something like 10 quizzes throughout the semester, I think that's just a lot less stress and more conducive to learning than having one or two big midterm exams. Let's just reflect a little bit on why we're here together. So it may be that you're here just to take a college physics course for the sector requirement. So Physics 8 meets the physical world sector requirement, and Physics 9 meets the natural science and math sector requirement. So that's terrific. So my terms are just that you put in a consistent 8 to 10 hours a week, each week total. That's the whole thing. That's coming to class, that's reading, watching videos, solving the problems, everything. Try to keep it consistent week to week. And in return, I'll do my best to make the course fun, informative, and stress-free for you. Now, you may be here because some kind of a college physics course is required for entrance to most graduate programs in architecture. And if that's true for you, I think this course is an especially good fit because we really try to tailor its content to your needs. We try to tailor its delivery to your visual learning style. Or maybe eventually to be certified as a practicing architect, you are going to take exams covering structures, heating and cooling systems, plumbing, electrical systems, acoustics, and so on. Or maybe because making a detailed energy model of a building depends on the physics of heat and light. All of those things make sense, and some of these topics, like the structures-related topics, are Physics 8 topics. All of the rest of the topics are Physics 9 topics. So things like electricity, fluids, acoustics, thermal modeling, and so on, that's all Physics 9 content. So, but I think more generally, you're here in this course, if you're an architecture major or in a related field, because many of you someday are going to design things that are going to exist, and they're going to be seen, and they're going to function in the physical world that surrounds us. And a better understanding of the physical world will make you a better designer of such things. So also, if you work with engineers on designs, then you may not be the person doing all of the detailed calculations. It may be that the engineer will do that for you, but you need to be able to ask good questions. And I think it's easier for you to ask good questions because an architect is often leading a team of people on a design. And you will be able to ask better questions, I think, of the technical people on your team if you all speak the same language. And I think that a solid grounding in physics helps you to speak that same language. So this semester, we'll be focusing on mechanics, which should prepare you well for the structures course that many of you will take as seniors, or it's likely that about half of you that are architects, that's true. So we'll be learning, or in many cases relearning, Newton's laws of motion. And you're going to exercise that mathematical side of your brain. And it may be, maybe you're a senior now, and the last time you took a math course was your freshman year. So often it's true that kind of mathematical side of your brain has had a couple of years to kind of be a little bit less exercised. So it's good, actually. One thing that really makes learning stick is if you allow it to sit for a while without using it, and then you wake it up and use it again, and especially if you use it again in the new context. So I think this is really going to wake up and exercise that mathematical side of your brain, and so I think it'll be a fun way to really solidify that math knowledge that you have maybe from your freshman year of college. So Professor Farley, who teaches structures, which is Arch 435 and 436 here, he tells me that he wants students to enter his course with a solid understanding of forces, torques, vectors, and trigonometry. And so one key goal of Physics 8 is to leave you very well prepared for his course. And he always tells me that the students who have come through this course have entered his course extremely well prepared for the learning that they'll do in his course. So if you are in that program, I really think this course is excellent preparation. One more thing I want to point out is, so we do ask you to do at home a combination of watching videos and reading the textbook before you come to class, so that we don't have to spend time in class going through step by step how you do everything you've seen at home for the first time, the tools that we're going to use in class. And then you can get started with the knowledge that you bring from home, and you can ask questions as you get stuck on things. So to give you credit for the work that you do at home, watching videos and reading the textbook chapters to try to make sure that the ideas have at least had a first chance to enter your mind before you use them in class with your classmates, you're going to fill out these online response forms. So the first one will be today. So after watching this video, you'll go to this URL, which is linked also from Canvas as a Canvas assignment, but it's positron.hep.upenn.edu/Q008. So instead of P for physics, it's going to be Q for questions. And here's what the page will look like. And so you say Physics 8-9 Reading Assignments page, and it's going to say you're not signed in yet. And then you'll see a little calendar, and there's a list of assignments. The first thing you're going to do is sign in. So you're going to go over here and sign in. So once you click sign in, you're going to enter the 8-digit student ID number that appears on your pen card. So there's a 8-digit number written in big numerals, and then sometimes in smaller numerals. There's like, 01, 02, 03, depending on how many times your pen card has been replaced. So just the 8-digit part. And you're going to type that in, and then you're going to click email new pin. So there's an email new pin button down here. Okay, and there's nothing confidential stored here. It's basically just a technique for turning your answers into an email. You'll see that in a minute. So then you're going to enter your student ID number over here. For instance, maybe you'll type in 1, 2, 3, 4, 5, 6, 7, 8, and you'll click email new pin. Okay, oh, by the way, this only works if I know that you're in the course. So if you just added the course like yesterday and I haven't noticed yet, then this won't work, and you'll have to write me an email reminding me to add you to the course. My little web form will email a 4-digit code, which is it's just a code that my program generates for you. So I don't want to store any confidential information that you generate. So this is just some little 4-digit number that I make up for you. And it's going to be emailed to whatever address I have on file from you. Usually it's like your pen key at sas.upenn.edu or your pen key at wharton.upenn.edu. Okay, then you're going to look for that email. So I look in my email, and there's an email from me to you. Of course, in this case, I'm you, so it's like from me to me. It says, hello, here's your name, your physics 89 pin is blah. Okay, so now I guess I will type this 4-digit number together with my ID number. I can type in I made up a fake entry for myself just to test the program. So I type in my fake ID number here, and I type in my fake 4-digit number, and then I like to check these little boxes that say remember me on this computer, because then I don't have to go through this the next time. It just remembers it as a little cookie in your web browser. And okay, so then you just click login, and after all of this, then you can type your answers into a little form, and it formats it into an email. So here, let's watch and see what the outcome of this is. So now it knows who you are. It says you're signed in as whatever your name is. And then we can go and click on the reading assignment for the first day of class, which is actually only a video assignment. And then we will see a form with a bunch of questions, not too many questions. So you see a form with a bunch of questions, and you want to type in your answers to the questions in these boxes. Now, this is not an incredibly smart web form, so it doesn't save as it goes along, so you actually might want to compose your answers in some program like Notepad or whatever, some text editor, so that in case my web form program somehow chokes, you don't lose what you've typed. But anyway, so you'll probably copy and paste into this form, and then we'll see what happens. So you put your answers in and you type submit. Okay, so here we go. I guess I typed American Ninja Warrior up here, and I guess I typed, we use 2 scales, one to measure the load that each support bears. I found it interesting to compare with my experience when moving heavy furniture with a friend. Kansas City Hyatt Regency skywalk collapse. And then, okay, I say please call me Bill or Dr. Bill if you prefer that. And some people, maybe your name, the registrar says your name is William, and maybe you prefer Liam. So you should tell me, please call me Liam. So if you think that the pronunciation of your name might not be obvious to me just from reading how it's spelled, then you can give me some hints how to pronounce it. After you've filled in your answers and clicked submit, my little program will send an email that looks as if it's generated from you to me with a carbon copy to you. And so again, it's really just a way of organizing the answers. I guess I could use Canvas for it, but I actually like putting it in my email, because then you'll notice that at least in the first few weeks of the course, I will write back to you. And if you've asked me a question as part of your answers, or if I find your answer especially interesting, or maybe in the first few weeks of the course I just want to say hello, this opens up a kind of email channel for us to discuss the course material. So I find that this, and I often do this with my train time, so the time that I spend commuting back and forth to Penn on the train, I often spend reading and responding to your answers to my reading questions. So this is another way for me to get to know you as an individual in the course. And actually, when people ask later for a letter of recommendation, I always look for every possible way that I can find that they distinguish themselves. And some people write really, well-reasoned, articulate answers to my physics questions in their reading responses. Not everybody does, but some people do. So if you do, I will certainly point that out. And sometimes it's fun to be able to describe for the graduate school that you're applying to, just how well-spoken you are in written language, how articulate you are at describing in complete sentences things that you're just learning for the first time. I'm always impressed by that. So you can see the whole output of this program that I've been describing is simply to create an email from you to me, carbon copy to you, that has the questions and answers formatted in kind of a standard format and with a very standardized subject line, and that makes it easy for me to grade because I can just search my email for all of the responses for a given date by searching on the subject line like this. So that's really all that's happening here. If you can't get this web form to work for some reason, then just write me an email with the questions and your answers. And if possible, try to use a similar, subject line. Like reading response for 2021-09-01. That makes it super easy for me to search for and process. Two topics that appear in Mazur Chapter 1 that could be useful are estimation and unit conversion. So let's try to combine them both in this question. Let's estimate the mass of water in a rooftop swimming pool. And you'll do another estimation on the first day of class. You will estimate the mass of the Great Pyramid of Giza. So, how are we going to do this? So I guess we can try to remember that mass is volume times density. So then we want to know what's the volume of water in our rooftop swimming pool, and then we want to know what is the density of water. We want to combine these things together. Now, I didn't give you any details about our rooftop swimming pool, and that's on purpose. So often the idea behind an estimation problem in physics is you want to work out an approximate answer, and maybe it's good enough if it doesn't have to be plus or minus 1%. Maybe plus or minus 25% is good enough. Maybe plus or minus a factor of 2 is good enough. Maybe plus or minus a factor of 3 or a factor of 5 is good enough. So we want to estimate roughly an answer to a question which may not be perfectly posed, just to get a rough idea of what value would be plausible. So then we'd say, okay, what's consistent with our expectation versus what would be incredibly surprising. We really want to double check whether we understand what's happening. So let's just consider the volume of a rooftop swimming pool. So how big, I guess we want to know how long one lane is. Let's say we want it to be a pool you can swim laps in. So if the sheer pool on the UPenn campus at the Pottruck gym is 50 meters long. But usually there's a divider up, so you can only swim in half of it. And one half actually is usually 25 meters, the other half is 25 yards. So let's say that our rooftop swimming pool will be 25 meters long, because that's long enough comfortably to swim laps. Now, I guess it could have been an Olympic-sized pool. We could have made it 50 meters long, but that would be pretty extravagant for a rooftop pool. Or we could have made it maybe just 10 meters long, but then, if you're going to go to the trouble to make a pool, maybe you do want it to be long enough that people can use it for exercise lap swimming. So I think this is a plausible number for the length. Then you say, well, how wide is it? Well, actually, Professor Farley built himself a pool that is 1 lane wide so that he or his wife can swim laps back and forth, for exercise in the morning. It's even a nice saltwater pool. But if you're going to put a pool on the roof of your high-rise building, it probably will want to accommodate more than one person swimming at a time. So I'm going to say maybe it's 10 meters this way. I mean, maybe it could be 5 meters. Could be 20 meters if it were like maybe designed for the swim team all going at once. But again, I think kind of reasonable in between value is something like 10 meters wide, because that would probably be like, what is that? That's probably like 4 or 5 lanes. I mean, even 5 meters wide might be plausible, but let's say 10. And then another question is, how deep is it? So you could have just 1 meter depth, and that's actually adequate. That's like the shallow end the whole way back and forth. The sheer pool on the Penn campus, it has a shallow end, which is about 1 meter deep, and it has a deep end, which is about 3 meters deep, and then the deep end sort of tapers. So you could pick a number of 1 meters or 2 meters. 3 meters would be the deep end the whole way. So I would probably say 2 meters deep But you could say 1 meter deep. That would be perfectly fine. I mean, just like this could have been 5 instead of 10. Maybe it could have been 20. I'm not sure it'd be 20, but it could be, probably could be 5 or 10. You know, maybe this could have been 50 if you're being super extravagant. Maybe it could have been 10 if you're really trying to save space. So again, all of these inputs, you know, it seems like we have a number of these inputs which, you know, maybe we could have made this one half as big, and maybe we could have made this one half as big or twice as big, and maybe we could have made this one half as big or twice as big. Although your estimate and my estimate probably won't be big all in the same direction or small all in the same directions. This is one interesting thing. You make an estimate and I make an estimate. We might choose different particular values, but if you choose one high and I choose, you know, you might choose one high and one low, and I might choose a different one high and a different one low, and it's likely that some of them will end up multiplying out to about the same volume. Okay, so this seems as if our volume is 25 meters times 10 meters times 2 meters, which is, let's see, 50 times 10, 500 cubic meters. Okay, and again, certainly we could have got a number that was 2 or 4 times bigger or 2 or 4 times smaller if we put in slightly different inputs, but it's a good ballpark number. What is the density of water? Well, you might remember that if you take a 1 cubic centimeter of water, let's see, I'll have to remember how to draw a cube. Okay, if you take 1 cubic centimeter of water, it has a mass of 1 gram, right? So that's kind of a familiar number from school days. And okay, so the density of water, a familiar number for the density of water is 1 gram per cubic centimeter, right? So we'll say, okay, this density is 1 gram per cubic centimeter. So we'll use that number, but before we do that, let's just build a little bit more intuition. So if we took, instead of 1 centimeter by 1 centimeter by 1 centimeter, suppose we took 10 centimeters by 10 centimeters by 10 centimeters. Let's see, so 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then I had to do the same thing in the third dimension. Maybe I won't bother, but you know. So if I took a 10 by 10 by 10, 10 centimeter by 10 centimeter by 10 centimeter cube of water, by the way, that's a liter, right? So 10 centimeters by 10 centimeters by 10 centimeters, that's a liter of volume. And if you take a liter of water, what is the mass of a liter of water? Well, if I told you it's a ton, you wouldn't believe me. And if I told you it's a gram, you wouldn't believe me. A liter of water turns out to have a mass of 1 kilogram. That sort of makes sense. You just think about how, you know, you have a 1 liter bottle of fizzy water or of soda or of milk. It makes sense. It weighs about a kilogram. And one more piece of kind of intuition. Suppose you replicate this 10 times. So if you took a 1 meter by 1 meter by 1, so here. So if we take 10 centimeters on a side and we cube that, this is of water, right? And if we take 10 centimeters on a side and we cube that, that is 1 kilogram of water. And you can say, actually, how can we do that? So you're just kind of waving your hands and doing that. Let's try to do it a little more systematically. So if we take 10 centimeters cubed is the volume, right? So we said mass is volume times density. If we take 10 centimeters cubed is the volume, and then times 1 gram per cubic centimeter is the density of water, then this is centimeters cubed upstairs, this is centimeters cubed downstairs, so we can cancel the centimeters cubed upstairs with the centimeters cubed downstairs. This is 10 to the 3 grams, so that's 10 to the third power grams, which is 1,000 grams, which is 1 kilogram. Okay, so I guess maybe that's not too surprising. Then we could say the same thing with 1 meter by 1 meter by 1 meter and multiply it by this same familiar density of water, which was 1 gram per cubic centimeter. So we can say 1 meter cubed, and then we're going to multiply that by 1 gram per cubic centimeter. And you say, well, I don't see now the meter cubed doesn't cancel with the centimeters cubed. Uh-oh, what do I do? Well, we can, so then notice that 1 meter equals 100 centimeters. And so therefore, 1 meter divided by 100 centimeters equals 1. And you know that you can multiply by 1 without changing anything. So we're going to find some clever way to multiply by 1 such that the units that we don't want cancel out, and we're left only with the units that we do want. So let's multiply by 100 centimeters divided by 1 meter. 100 centimeters equals a meter. So 100 centimeters divided by 1 meter is just 1. We can multiply by 1. It doesn't change anything. That's not quite good enough because we have meters 3 times here, we have centimeters 3 times here. So we're going to cube this. Now that we've done that, now we have meters cubed upstairs, we have meters cubed downstairs. So we can cancel that meter cubed with this meter cubed. And we have centimeters cubed upstairs, we have centimeters cubed downstairs. So we can cancel that centimeters cubed with that centimeters cubed. You have to be careful. This cube is still here multiplying the 100. Okay. So this is 1 gram times 100 cubed. What is 100 cubed? Well, you know 100 is 10 to the 2 power. So 100 cubed is 10 to the 6th power. Right? 100 times 100 is 10,000 times 100 again is a million. So this is a million, or it's 10 to the 6th. So this equals, so this is 10 to the 6th grams. And then, okay, maybe that's not too useful. Yeah, so now we can multiply this by 1 again because maybe you want to express it in kilograms. So then you say, well, 1 kilogram is 1,000 grams. Okay, and 1,000 is the same as 10 to the 3, so maybe in this case it's more convenient to say 10 to the 3 grams. And then we can cancel grams downstairs with grams upstairs, and then 10 to the 6th divided by 10 to the 3. So a million divided by 1,000 is 1,000, you know that. So here's our 10 to the 3. So then what's left upstairs is 10 to the 3. So this is 10 to the 3 kilograms. That's 1,000 kilograms. That turns out to be 1 metric ton. So the mass of a meter by a meter by a meter, so the mass of a cube of water, which is 1 meter on each side, is 1 metric ton. That's maybe that's not surprising. I mean, if you took that much water, it would weigh a ton, right? So it seems like if we have 500 cubic meters of water here, we think we're heading for an answer of 500 tons. But let's be more careful. So what did we do over here? We used our kind of secondary school memory that the density of water is 1 gram per cubic centimeter. And we said, okay, well, how about 10 centimeters on a side, all that cubed. And we said, okay, that's a kilogram of water. And how about 1 meter of water on a side as a cube? Well, that is a metric ton of water. Okay, but let's go back to this statement here. So we say mass is volume times density. So we're going to say the mass of the swimming pool is, right, so it is 500 cubic meters. And then the density of water, we said, is 1 gram per cubic centimeter. But you say, well, I have a problem here because I have cubic meters upstairs and I have cubic centimeters downstairs, and I want things to cancel out and just leave me units of mass. So how am I going to make that happen? Well, let's find a way to multiply by 1. So let's say we want the mass in kilograms. So we can say, well, let's multiply by 1 kilogram per 1,000 grams. Okay, that'll get me kilograms upstairs. It still hasn't solved this problem. And then let's say, let's multiply by, see, now I could say 1 meter divided by 100 centimeters. Or I could do that multiple times. But this makes things even worse, because now I have even more meters upstairs and even more centimeters downstairs. So even though 1 meter divided by 100 centimeters equals 1, that's not the useful way to do this. I have to do it the other way, where I say I have 100 centimeters divided by 1 meter. That's a name for 1, so I can multiply by 1. 1 is the multiplicative identity. But I want to do this not once, I want to do this 3 times, so that now I get rid of the cubic meters upstairs and I get rid of the cubic centimeters downstairs. So this meter cube cancels with this meter cube, and this centimeter cube cancels with this centimeter cube, and then this gram cancels with this gram. And this is good. I have an answer in kilograms. So it seems like sometimes it's useful to use scientific notation, you know, you just use exponents. So we could say, well, 100 cubed is 1,000,000, and that's divided by 1,000, so that's 1,000, and this 500 is 500,000. Okay, we could do that. Or you could say this is 500, and then this is times, this is kilograms, and this is 10 to the 3 downstairs, and then this is 10 to the 2 cubed, so 10 to the 2 cubed is 10 to the 6th. So this is 10 to the 6th. And now we have 10 to the 6th upstairs and 10 to the 3 downstairs. That leaves us with 10 to the 3. So that equals 500 times 10 to the 3 kilograms. That's fine. That's an acceptable answer. 500 times 10 to the 3 kilograms. You could also write this as 5 times 10 to the 5th kilograms. That's fine, because you could bring those zeros in there. Sometimes it's nice to have like the, you know, the exponent be a multiple of 3, because then, you know, I don't know, you might say, well, kilograms, 10 to the 3 kilograms is like megagrams. Nobody says megagrams. Megagrams are actually metric tons. So another thing we could do if we wanted to is we could multiply by 1 metric ton is 1,000 kilograms. That's the name for 1. So then we would have our 10 to the 3 kilograms cancel with our 10 to the 3 kilograms, and the answer would be 500 tons. I like to spell ton. You know, I'm used to writing ton like this, T-O-N. But when I mean a metric ton, I write it the British way. I don't know if everybody does that, but I do it because it reminds me that I'm talking about metric tons. So it seems like using these dimensions for the pool, and again, assuming it's fresh water, I guess if it were salt water, it might be a few percent more dense, although at the level of our estimate, a few percent more dense isn't going to make any difference. So I would say a plausible value for the mass of the water in our rooftop swimming pool is like 500 tons. Now, an equally plausible number would be like 1,000 tons or 200 tons, maybe even 100 tons. So anyway, but I would say probably bigger than 100 tons and probably no more than 1,000 or 2,000 tons, because there's only so far we could stretch these factors. But anyway, my estimate for the mass of a rooftop swimming pool is 500 tons. And so part of it is coming up with plausible input numbers. And part of it is remembering things like, okay, to get the mass, I have to know how big it is, and I have to know the density of water. And then part of it is then once you have numbers that have units, dimensions associated with them, the systematic way to put them together in a way that avoids mistakes is to use this cancellation and to keep multiplying by 1. You find ways to multiply by 1 until the units that you don't want disappear and you're left with the units that you do want. And so then you systematically go and cancel things from the numerator and denominator. And then another thing that you saw us do at the beginning is we said, well, before we put a whole bunch of numbers together, let's use our knowledge that the density of water is 1 gram per cubic centimeter. And then let's ask, so the mass of 1 cubic centimeter of water is a gram. And we say, okay, the mass of a cube of water, which is 10 centimeters on a side, that turns out to be a liter. The mass of a liter of water is a kilogram. And then the mass of a cube of water, which is 1 meter on a side, is a metric ton. So he said, okay, now we said a cubic meter of water has a mass of a metric ton. So if we can get a number for the volume in cubic meters, which you might have some intuition for, then we can directly connect that to metric tons. And I think, so that kind of gives us a check. In case we messed up our multiplication, that gives us kind of a reality check. It's often useful to approach something more than one way and remember your answer both ways and see if they agree with one another. So what you're going to do in class on the first day is you will say the Great Pyramid at Giza has a it's a pyramid with a square base. So I guess it looks something like this. Something like that. Okay. And then you'll take the formula for the volume of a pyramid like that. I think it turns out to be 1/3 times the base times the height. And then you'll have, that gives you a volume, so you have some estimate for the base area and you have some estimate for the height. And then what's it built out of? It's some kind of stone, so then you have to say, well, I wonder what kind of stone it is, what's a plausible value for the density of stone. And you'll come up with a number, and then you can look and see what the Wikipedia says, and you can see how close you came with your estimate. By the way, one useful trick to know is that your preferred search engine, for example Google, probably knows how to do unit conversions for you, so sometimes it's useful. Well, for instance, I can say, well, you could, yeah, okay, we say 25 meters times 10 meters times 2 meters times 1,000 kilograms per cubic meter, which is the way you write the density of water in SI units, we'll see. And Google says, oh, that's 500,000 kilograms. 500,000 kilograms. So that was useful. And then you could also ask it, well, by the way, what would 5 times 10 to the 5th kilograms be in pounds? And it says, oh, it's about 1.1 million pounds. Well, that's kind of interesting. So, you know, 5 times 10 to the 5th kilograms in pounds, and Google will convert it for you. So sometimes that's convenient. Or it's also sometimes a way to check. If you converted it by hand, you can see if Google agrees with you. Okay, so I will see you in class on Wednesday.